Now, I'll leave the question open. That's fine. I mean, I made you think about this. That's the main idea here. Okay, that's called active learning, making you think about what you learn. So now here's what we have. Oh no, I cannot see the question now. Shoot. Okay, give me a second. Here we go. Okay, so we have in a random order completely. Wink, wink. Magnesium 2 plus, and then we have sodium plus, and then we have neon. We have neon, and somehow it got lost when it went to the options. Neon, and then we have fluorine minus or fluoride ions. Okay. Now, what you want to do here is, oh, give me a second. Let me maximize this. Okay. What you want to do is first you want to count the number of protons. Okay. So number of protons is the atomic number, which is the identity of the element. Okay. So magnesium, how many protons do we have? In magnesium, we have how many protons? Everybody. 12. Thank you. How do you know that? Go to the periodic table. That's the atomic number, that we have for magnesium. Sodium, what's the atomic number or the number of protons? Everybody. I didn't hear you. Thank you. There you go. My favorite group over there, wherever you are. All right. Anyway, so we have 11. And neon, how many protons? Fluorine, how many protons? 9. Thank you. Now count the number of electrons. Okay. Magnesium 2 plus. When it is magnesium, it has 12 electrons and it's neutral. But magnesium 2 plus has 2 less electrons than the number of protons. Therefore, it should have how many electrons? 10. Thank you. 10 electrons. What about sodium plus? How many electrons? 10. Neon, how many electrons? Fluoride minus, how many electrons? 10. There you go. They all have the same number of electrons, meaning these 10 electrons are filled to the same shell in all 4 cases. Okay. But magnesium 2 plus has the greatest number of protons in the nucleus. Therefore, these 10 electrons are more strongly attracted to the magnesium nucleus than any other nuclei over here. As a result of that, the electron cloud of magnesium 2 plus will be the smallest because these electrons are more strongly attracted to the nucleus there. And then in fluoride minus, you have the least number of protons out of these guys. Therefore, least positively charged nucleus. Therefore, those 10 electrons are more spread out in fluoride compared to everything, all the other species. Therefore, fluoride minus will be the largest. Okay. So if you arrange them one more time, magnesium 2 plus will be the smallest. Why? The greatest nuclear positive charge with the same number of electrons, and then sodium plus, then neon, and then fluoride minus or fluoride ion, because you have the least number of protons, means the least positively charged nucleus in fluoride. Right? All right. What questions, concerns, comments do we have at the moment? Anything? Any questions at the moment? Diego, how are we doing here? How are we doing here? Okay, very good. I'm sorry for picking you. All right. Anyway, please, if you have any questions, I'm trying to pick from people so that I can get you to ask questions, but it's okay. Now that is that. Again, this is about the size of the atom again. All right. Now, what I want to do is just to recapitulate what we have done on Tuesday. Okay. Here's what we did towards the end of Tuesday's lecture. Okay. So these elements are in the same period. We saw that when you go across the period, the size of the atom decreased. Why? The electrons are filled to the same shell, but the number of protons in the nuclei increased from lithium to neon. Okay. Therefore, because you have the greatest positive charge in the neon nucleus, the electrons are more strongly attracted to neon nucleus. Therefore, it's going to be the smallest. Okay, that's how we explained why the size of the atom decreases across the period. Okay. And now the next thing I want you to do is I want you to think about how the potential energy of these electrons, it's called P dot E dot, okay, changes across the period from lithium to neon. Okay. We go from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay. So when you go across the period, how do you expect the potential energy to change? Go ahead. All right. And then here are our responses. Okay. So most of us said lithium has the highest potential energy and neon has the lowest potential energy. In other words, if we go back to our notes here, so from lithium to neon, the potential energy decreases. It's not necessarily linear, but for the first approximation, we know it decreases. Okay. Now, why does it decrease? Who wants to tell me why does it decrease? Anybody? Why should it decrease? Carter? That's it. Thank you. So neon has the greatest number of protons in the nucleus. Therefore, these electrons in neon are more strongly attracted towards that nucleus. Remember the mantra, the stronger the attractive interactions, the lower the potential energy. And that's why neon has the lowest potential energy and lithium has the highest, because lithium has the least number of protons. Therefore, those electrons are least attracted to that nucleus compared to neon. Okay. Anyway, so but I mean, if you want to be more technically correct, I would have 0 somewhere up above here, because we're talking about attractive interaction, interactive interaction. I'm sorry, attractive interactions here. Too much coffee. I'm sorry. All right. Anyway, do we have any questions, concerns, comments at the moment? Anything? Any questions, concerns, comments? All right. Now let's make another prediction. Okay. Now, there's something called the ionization energy. Okay. And that is the energy required to remove electrons. Because when you remove electrons, you're going to give the atoms or that species a charge, meaning making it an ion. And that is what we call ionizing. Okay. Now, what I want you to do is I want you to think about the energy required to remove just one electron. And that is called, anybody? What do we call that? It's called, it's an ionization energy. Just because we're talking about only one electron, that is called the first ionization energy. Thank you, Ethan. Yeah, and I saw the hands as well. Yeah. So what we want to do is we want to predict how the ionization energy changes across a period now. Okay, we'll deal with the same periods. We are in the second period now. Let's call this IE for ionization energy. I'm going to add F here for the first ionization energy. All right. So if I define it, first ionization energy, okay, O F I E. All right. Anyway, so what I want you to do is I want you to predict how the first ionization energy changes across the second period, from lithium to beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Go ahead. What do you predict? That should be enough time for discussion, I think. Before I look at your answers, I want to mention one thing. I mean, I like the things I'm hearing from your groups. Okay. But I want to correct some wording here. I saw that some of us still, use the terms like intermolecular forces. We are not dealing with molecules here. There are no intermolecular forces, so there are no IMFs here. Okay. What we have is attractive interactions between the electrons and the nucleus. And that is becoming stronger or weaker based on the number of protons we have in the nucleus. That is, I just want you to correct that term, but I know what you think, and that is correct. Your thinking is absolutely correct. But if you can correct that wording as well, that would be fabulous. All right. Anyway, the question. Okay. So let's see. I'm going to close this question in 5, 4, 3, 2, and 1. And here are our responses. All right. So most of us said the ionization energy, it will be easiest to remove an electron from lithium, and it will be hardest to remove an electron from neon, meaning Neon will have the highest first ionization energy, and lithium will have the lowest first ionization energy. And that's the correct answer as well. 70% of us are already there. Okay. Now, that is absolutely correct. Okay. That's my prediction as well. Because you have least attractive interactions between the electrons of lithium and its nucleus. Okay. It will be easy to take away an electron from lithium compared to taking away an electron from somebody like neon, because it has more protons, more attraction towards those electrons. Okay. Therefore, we can predict that the ionization energy increases from lithium to neon. Okay. It doesn't have to be necessarily linear, okay? But in general, it needs to increase. That's all I'm saying here. I'm not saying it's linear, it's just increasing across the period. All right. What questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? Okay. So that's our prediction. So let's look at some data as well, okay, to see whether our prediction is correct. By the way, we made this prediction based on the shell model. Okay. Electrons are filled to the same shell across the period. Therefore, when we increase the number of protons in the nucleus, the electrons are more strongly attracted to that nucleus. Therefore, the ionization energy increase. That's our prediction. And let's see how close we are to the actual values. Here we go. Okay. And these are the data. Guess what? When you go from lithium to neon, you see that the first ionization energy increase across the period. Same thing with the first period from hydrogen to helium, it increased. Why? The number of protons in the nucleus increased. And from sodium to argon, they're in the third period. Okay. Again, it increased. Why? Electrons are filled to the same shell. Because you are increasing the number of protons in the nucleus, it's going to be harder for you to remove those electrons because they are more strongly attracted to that nucleus. Okay. The same thing with potassium to krypton as well. All right. Do we have any questions, concerns, comments? Okay. This is nice. The shell model works so far really nicely. We were able to explain the size trends, periodic sense of trends of size, and also we were able to explain the first ionization energy trends as well. Yeah. Any questions, concerns, comments at the moment? Anything? Okay. Now, let's see. Next thing, what I want to do is, give me a second. Let me clear my doodling. Right. Here you go. Let's try this. Let's combine those two. And this is an example exam question. I'm not saying this is going to be on the exam, but you should be able to do something like this. That's beautiful. Okay. Most of us said carbon atom is bigger. Okay. Okay. Why? Carbon atom has, so carbon and oxygen, they are in the same period, meaning electrons are filled to the same shell. But carbon has less number of protons in the nucleus. As a result of that, these electrons are less attracted or weakly attracted to the carbon nucleus than the oxygen nucleus. Okay. Therefore, the carbon will be larger compared to oxygen. Okay. Due to the same reason, it will be easy to remove an electron from carbon because the electrons are weakly attracted to the nucleus. Therefore, it is easy to remove an electron as well. Therefore, the first ionization energy will be lower for carbon compared to oxygen. Okay. And then this diagram says same thing over here. So this is shell 1. Okay, this is shell 2. Current shell model. This is all we have. These are the energy levels we have according to the shell model. All right. So you see that in the carbon, the electrons are further away from the nucleus because nucleus is down over here, right? Right. Over here for oxygen. Right. This shell 1 and shell 2 for oxygen over here. Okay. Because you have a greater positive charge in the nucleus of oxygen, these energy levels are lowered, okay, in oxygen compared to that of carbon. All right. Any questions, concerns, comments at the moment? Anything? Do we have any questions, concerns, comments? Okay. All right. So with that, please, if you have anything, ask from somebody. Okay. You don't have to ask me. Ask from your neighbor. Ask from a learning assistant. Okay, when I walk around, just grab me and then ask. You can ask me during that time as well if you don't ask in front of the whole class. I totally get it. Okay, so anyway, just ask. All right, now 90%, which is great. So let's do this. Now, what we're going to do next is, okay, so far the shell model worked fine. Okay, we were able to explain the size and the first ionization energies. Now we are going to move on to the last technique in Unit 2, Module 2. Actually, I think this is the last technique in Chem 151 that we're going to talk about. Anyway, let me see if I'm wrong. Okay, I'm gonna think about it. Okay, anyway, and this is called photoelectron spectroscopy. Okay, the thing about the photoelectron spectroscopy is it gives you the ionization energies of all the electrons of an atom, not just the first one, but all the electrons of an atom. Okay, and then I want you to pay attention to a few things here. On the y-axis of the photoelectron spectrum, we have, what do you say? I don't know whether you can say it. Yeah, the number of electrons. Okay, and on the x-axis, we have the ionization energy. And then I want you to pay attention very closely. The ionization energy increases from right to left, which is weird. Okay, so it increases from right to left. Okay, you have the higher ionization energies on the left and lower ionization energies on the right, which is kind of, reversed with respect to what we are used to. Oh, anyway, now let's start with something, the simplest atom, hydrogen. Okay, what do you expect to see in hydrogen? We're going to see peaks here. Okay, that's like in any spectra, we're going to see peaks. How many peaks do you expect to see? How many? One. Why one? That's just one electron, one shell, one electron, right? So there's going to be one peak over there. Okay, they're going to look like Christmas trees now. Okay, all right. By the way, Costco already has the Christmas trees up. Seriously. All right. Anyway, so yeah, this is what we expect to hydrogen. Okay, because all the electrons are filled with the same shell, just one electron. Okay, therefore just one peak. Now, what about helium? How would the helium photoelectron spectrum differ from that of hydrogen? What do you think? That question, okay? So let's see. I saw some of your diagrams. All right. How many peaks for helium? Thank you. One. Why one? It has two electrons. Why only one peak there then? Why only one peak even though it has two electrons? Because they are filled, those two electrons are filled to the same shell. Okay, for that reason, we're going to still see only one peak. But here's the difference. The ionization energies of those electrons will be greater now. Why? Helium has more protons in its nucleus. Look at this. Yes, helium. You see that the ionization energy increased from 1 point something. By the way, don't try to memorize the ionization energies. I have no clue what they are. I know that they increase. That's all I know. Okay. So helium, it went up to 2.37. Okay. For hydrogen, it was 1.3. And for helium, it went up to 2.37. Why? There are more protons in the helium nucleus. Therefore, the ionization energy is higher for helium. Okay. And also the peak height increased because peak height is related to the number of electrons it has, which is 2. It doubled. All right. Now, what about lithium? Can you draw the lithium photoelectron spectrum on your whiteboards? What do you expect to see? Go ahead. By the way, you might be asked to draw photoelectron spectra of elements. Beautiful. All right. So when you go from helium to lithium, how many peaks do you expect? 2 peaks. Why 2 peaks? Why do we expect 2 peaks? Any? 2 shells. Thank you. Okay, each shell has its own energy, right? Therefore, you're going to expect 2 peaks. Okay, so in the first peak, you're going to have 2 electrons. Okay, that's the first shell. And in the second shell, you're going to have only 1 electron because there's only 3 electrons in lithium. Okay. In the first shell, there's 2. And in the second shell, there's 1. It's like that. All right. Do we have any questions, concerns, comments about this? Anything? Any questions about that? Okay. And then I'll do one for you. I'll do beryllium. Okay, the next one. So beryllium has 2 electrons in the second shell. Therefore, you're going to say that. Okay. Now, what I want you to do is I want you to draw on your whiteboards the photoelectron spectrum of carbon. Go thinking, okay? So according to the shell model, all right, carbon is in the second period, meaning it has 2 shells, right? And in the first shell, you can only have up to 2 electrons. Therefore, I'm going to draw a Christmas tree there. Okay, 2. And then in the second shell, I have 4 electrons. Okay, so I should see a peak twice as the first one. Okay, but I have 4 electrons there now, right? Because altogether we have 6 electrons in carbon. So the 4 electrons will be in the second shell. So this is what we expect according to the shell model. All right. What questions, concerns, comments do we have? All right. I see some smiles. All right. You know something that I don't. All right. Any questions about this? Are you okay with this? Because I see that you do something else on your whiteboards. Cole, you have something else, right? Why? What? Are you saying I'm wrong here? Look at this guy. Right? Oh, so anyway, let's do the experiment. Okay, so let's do the experiment. So if you do the carbon atom, oh, look at that. This is what we get. Yeah, so I'm wrong. Okay, so it's more correctly, the shell model fails. That is what is happening over here. Okay, so as scientists, okay, when one model fails, what do? Anybody? Yeah, they modify that. All right. So what they do is they modify the shell model and called it. Anybody? Do you know what they called it? Modified shell model. Very creative. I know. All right. Anyway, so in the modified shell model, you have what we call subshells. All right. So the shell 1 can only have 1 subshell, and that is called S. Okay. But shell 2 can have 2 subshells. They are called S and anybody? And P. Okay. So this is shell 1, and we call it 1S. And then this is shell 2. This is 2S and 2P. Okay. Now, give me a second. I'm not done. Right. And a second. And the third shell has how many subshells? Anybody? How many subshells do you expect to have in third shell? 3 subshells. And they are called S, P, and D. Thank you. Let's go to the 4th shell. How many subshells do you expect in the 4th shell? 4. What do you call them? S, P, D, and F. Thank you. Maybe, this has started to sound familiar to you now, right? Anyway, so one more time. Shell 1 has only 1 subshell that is called S. Okay. It can have up to 2 electrons. And then the second shell has 2 subshells called S and P. S can always have 2. P can have up to 6. Okay. Third shell can have up to 3 subshells. They are called S, P, and D. S is 2. P capacity is 6. And D can have up to 10. Okay. And the 4th shell can have up to 4 subshells. They are called S, P, D, and F. S can have 2. P can have 6. D can have 10. And F can have, what's the capacity of F? It's 14. Thank you. It's 14. Anyway, so now those are the capacities of the maximum number of electrons that can be accommodated in each subshell. All right. Now going back to what we noticed here before. Now we got this for carbon. All right. If you write this separately, we see that carbon has 1s2, 2s2, and 2p2. What did I just write here now? What is this? Thank you. This is called the electron configuration of carbon. Okay. And this is where it is coming from 40 electron spectra. Okay. You might have memorized this before at your high school level, but this is where it is coming from. All right. Let's do another one. Can we draw the 40 electron spectrum of nitrogen? Now, here's what I would do. Okay. So for nitrogen, right? Nitrogen has 7 electrons. Okay, how do we know? The atomic number of nitrogen is 7. All right. So if I write the electron configuration of nitrogen, so first electrons will be filled to 1s because that's the lowest energy orbital or the subshell. Okay. Then we have the second shell. We have 2s and 2p. So in the second level is 2s, and then we have 2p. And then we have 3s, okay, and then 3p, okay, and so forth. Okay, so energy increases in this way. Okay, energy-wise, this is 1s, 2s. You don't have to do this, but this is going to answer one of your questions from last night assignment. Some of you had problems with this, 3s and 3p, okay. So the second energy level is the 2s. It can have only up to 2 electrons. Okay, that's why the answer for that particular question that you know what I'm referring to is 2. Louis? Yeah? Yeah. Okay. Now, anyway, so that's an extra thing. Okay, I just want to point that out. Now, the other thing I want to mention here is, so we have 7 electrons in nitrogen. So first, we're going to have 2 electrons in 1s, because that's the maximum 1s can have. Then 2 electrons in 2s, because that's the maximum that we can have in 2s. And now we have 4 electrons. That means we have 3 electrons left. Those 3 must go to 2p. Okay. And we don't even need these guys over here. Therefore, the electron configuration of nitrogen is 1s2, 2s2, 2p3. Okay. And if you draw the 40 electron spectrum, it's going to look something like this. Okay. And we can even draw 1s2, 2s2, and 2p3. Do we have any questions, concerns, comments at the moment? Anything? All right, let's do one last thing, then we're done. All right, let's draw the 40 electron spectrum of sulfur. So sulfur has 16 electrons. Okay, sulfur has 16 electrons. That's the atomic number of sulfur from the periodic table. Okay, now when we fill the electrons, we will first fill the electrons to 1s, then 2s, then 2p, then 3s, then 3p, and so forth. Okay, so 16. First, I'm going to get 2 electrons in 1s and 2 electrons in 2s, and the 2p can only have up to how many electrons? 6. Okay, 6. Now I have already 10 electrons. Okay, and 3s can have only up to 2. Now I have 12 electrons. Therefore, my p should have 4 electrons. Therefore, that should be my electron configuration of sulfur. Now, if you draw the 40 electron spectrum, so here's 1s, we're going to have 2 electrons there. And then I'm going to separate 1s from 2 because these are 2 different shells. Okay, 2s have 2 and 2p has 6. Okay, notice how I separated my first shell from the second shell because there's a large energy gap between the shells. But within the subshells, the energy gap is smaller. And then we have the third shell. Okay, we have 2 electrons in 3s, and then only 4 electrons in 3p. So this should be my 40 electron spectrum for sulfur. All right, what questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? All right. Now, there's something else we need to appreciate here. Okay. Now, when it comes to chemistry, chemistry involves only the outermost shell. Okay. Only the outermost shell. Okay. So the outermost shell is which shell here? What's the number of the outermost shell of sulfur? Yeah, it's 3, right? It's the third shell, is the outermost shell. Okay. And that outermost shell is called, anybody? It has a special name. It is called the, thank you, it's called the valence shell. valence shell. Okay. And then all the other shells inside that, okay, all the other shells are called the core shell. Okay. So the core shell of sulfur is up to this point over here. This is called the core shell. And core shell is always filled, completely filled, and it has a noble gas configuration. For example, in sulfur, we have 1s2, 2s2, 2p6 core shell. And which noble gas is that? Anybody? 1s2, 2s2, 2p6, or 10 electrons are filled. Which noble gas has 10 electrons? Neon. Thank you. So when we write the electron configuration of sulfur, we can also write neon core shell to indicate what we have in the core shell. And then the valence shell configuration, which is 3s2, 3p4. That's called the shorthand notation or noble gas notation for electron configuration. All right. What questions, concerns, comments do we have at the moment? Anything? Okay. So with that, let's have some fun with this. Oh, before we have fun, I'm going to break your heart a little bit. Okay. Now we know that we modified the shell model because shell model failed. It turns out even the modified shell model is not completely correct. Sorry. Okay. And the most accepted model now is called the quantum mechanical model. Okay. According to the quantum mechanical models, even the subshells divide into sub-subshells. Okay. For example, the P subshell can be divided into 3 sub-subshells called PX, PY, and PZ. Those are also known as orbitals. Okay. And the D subshell can be divided into 5 sub-subshells called DC squared, DS squared minus Y squared. And there are 5 of them like that. Okay, which we don't need to know. Anyway, so each subshell or each orbital, this is also called sub-subshells are also known as orbitals, has an occupancy limit of 2 electrons. It can only have up to 2 electrons. Okay, and there's a reason for that, and that has to do with the Pauli exclusion principle, okay, which we are not going to go into. You can forget about this slide and this slide as well. Pauli exclusion principle said that so orbital is a region of space where the electrons can be found. Okay, in an orbital, we can only have the electrons need to have different spins. Okay, so the two spins possible are spin up and spin down. But if you try to include the third electron there, that's going to be either spin up or down. Therefore, it's not gonna work. Okay, because you cannot have 2 electrons with the same spin in a given orbital. 1. Okay, and here are our response. Look at this. This is beautiful. Okay, 97% of us said this is the configuration, and that's the correct answer as well. All right. So again, remember the highest ionization energy is for the first shell. This is 1s2, then 2s2, 2p6, and 3s2, and 3p4. This is the same thing we did actually, which is great. Anyway, do we have any questions, concerns, comments at the moment? Anything? Okay. Let's do 2 other questions from 4 electron spectra. 4, 3, 2, and 1. All right. And here are our responses. Look at that. Okay. Now let's look at this. Okay. So valence shell is the outermost shell, which is going to have, which will have lower ionization energy. So which is going to be this valence shell. Right. It has 6 electrons. And then everything else is called the core shell. Okay. And the core shell seems to have 10 electrons. Okay. Which is the neon configuration. That's it. Now let's see what they're asking. There are 6 electrons in the valence shell. That is correct. There are 10 electrons in the core shell. 30 of us did not say that. Anyway, that's okay. And then the atomic number is 16. How do we know that? This is a neutral atom. You are told it's a neutral atom. And altogether, if we count the electrons, it adds up to 16. Therefore, the atomic number must be 16 for this, meaning this must be sulfur. Yeah. All right. Any questions, concerns, comments about this? Anything? Yeah. What's your name, miss? Sammy, go ahead. Oh, yeah. How can we tell the atomic number? Okay. So you are told in the question is a neutral atom. This is the 40-electron spectrum for the neutral atom, which has 16 electrons. That means it should have 16 protons. That means that's the atomic number. Yeah. Any other questions, concerns, comments? Okay. Now, with that, let's do. All right. So no, I think that should be enough time for that question. Okay. Things are taking a little bit longer than it should. That's okay. So I'm not going to close the question yet. Okay. But I'm going to go over it myself so that you can see the way I think about it. All right. So whenever you are asked to write the electron configuration of an element, go to the periodic table. Okay. Let me go to the periodic table over here. Okay. Now you are asked to write the electron configuration of germanium, which is over here. Now, here's what I noticed. To get to germanium, I need to completely fill 1, 2, 3, the third shell, which has the argon electron configuration, meaning germanium has the argon core shell configuration. Okay. And then in the fourth shell, I have first two groups filled. First two are my S subshells. Okay. So we have 4s2 filled. Okay. And then I have these guys filled. Here's the caveat. These guys are not 4D. These are 3D. Okay. These are 3D. And we have 10 electrons in them. Okay. We have filled up to 3D10. And then in 4p, we need to fill up to the second one, which is 4p2. Therefore, it should be 4p2. Now, if you write the electron configuration for germanium like this, that is fine. It is not the most accurate way of representing it. The most accurate way of representing it is you write the argon, which is the core shell. And then you're going to write 3D first, 3D10, then 4s2, 4p2. In the valence shell, which is the fourth shell of argon, you only have 4 electrons still, not 14. It's just 4 electrons. Okay, that's how you do that. But if you don't do that, I mean, if you don't swap that 3D and 4s, that is fine. Okay, I mean, as long as you have these electrons filled correctly. All right, what questions, concerns, comments do we have about this? I have a video, I mean, going over some other elements as well. I mean, I will post that on D2L, a supplementary video. Okay. So, yeah. Now, the caveat here is this, right? You see that before you fill 3D, 4s is filled. Okay. Even though 4 is in a higher shell. Okay. So 4s is filled before the 3D. The reason is 4s has a little part of it that has a lower energy than 3D, and that's why it is filled before 3D. Okay, but once it is filled, larger region of 4s still has a higher energy than 3D, and that's why I rearranged that to be like 4s2 and 4p2, right? 4p2 at the end. Okay, that's a rearrangement, and that is something we have to get used to. All right. Any questions, concerns, comments about this? Anything? I will post a video as well. We need to practice a little bit over here because of this 3D swap, but that's it. But that's something we can get used to. Okay. I'm going to delete. Yeah. Yes, from the nucleus. Yeah. Yeah, 4. You will always remove electrons from the outermost shell, which is going to be the fourth shell. Yeah, exactly. Yeah. So, I mean, if you remove electrons from here, you will first remove electron from 4p before 4s, because 4p is the outermost one. Yeah, we'll do some of those as well a little bit later. All right. So, just to remind us, chemistry involves the valence shell. So when we write the electron configuration, that's why we write the core shell with the noble gas configuration, and the valence shell, we write it out to know what exactly happening there. Okay. So for an example, for oxygen, we can write the electron configuration like this. And then what we want to know is the outermost electrons or the valence shell electrons are the ones that is involved in bond formation or in chemistry. Okay. Now, the question is about the number of bonds oxygen form. How many bonds does oxygen usually form, the common bonding pattern? How many bonds? How many bonds does oxygen form, everybody? 1, 2, 3. Which one is it? 2 bonds. Okay. How do you know that? Noble gases first, they form 0. Move on over, fluorine, chlorine, bromine. They are one group away from the noble gases. They form 1 bond. Move on over, we have oxygen, sulfur, they form 2 bonds. Okay. And now, what we want to do is we want to explain this. To do that, I want you to do something for me. Okay. Now, valence shell for the non-metallic elements has a maximum capacity of 8. All right. For example, if you take oxygen, right? Oxygen electron configuration is helium. Okay. Then we have 2s2, 2p4. Okay. So the valence shell, which is the second shell, can have up to 8, but we only have 6. So how many vacancies are there in the valence shell of oxygen? Everybody, two vacancies. We can have 8. We only have 6. Therefore, there are 2 vacancies. Okay. And therefore, oxygen, you should match with 2. Now, what I want you to do is I want you to do that for the other elements over here as well. Go ahead. And here are our responses. Okay, look at this now. Carbon has 4 vacancies. The common bonding capacity of carbon is also 4. Hydrogen has 1 vacancy. The common bonding pattern is also 1. Nitrogen has 3 vacancies. Guess what? The common bonding pattern is 3. Oxygen has 2 vacancies. Commonly, oxygen form 2 bonds. Fluorine has 1 vacancy. It forms 1 bond. Bromine, 1 vacancy, 1 bond. Tellurium, 2 vacancies, therefore it should form 2 bonds. Okay. So the number of vacancies in the valence shell is same as its common bonding capacity. That's the method.